Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to introduce this next section. We're going to be discussing and introducing frequency analysis. So in this topic we will review interpolating and least squares best fitting polynomials. We will describe how all of this is being done in the time domain. So this is time domain analysis. We will discuss how this may be suboptimal, especially if we have periodic signals. We will therefore describe the upcoming lectures where we will be transforming from time domain to the frequency domain, and then rather than analyzing the time domain signal, we will analyze the signal in the frequency domain. However, we'll conclude by giving a quick review of the properties of vectors and see that functions have these exact same properties. What that means is that functions, sine of x, cosine of x, 3.5 times sine of x times t times e to the negative t, all of these are essentially vectors, but rather than being indexed by an integer from, say, 1 to 8 for an 8-dimensional vector, instead these vectors will be indexed at a value t, where t could be any real number or any number on a specific domain. So up until this point, we have assumed that we are periodically sampling data in the time domain. So at some point in the past, we started sampling a value from a sensor, and we are storing those and we are analyzing that data. Now, our analysis up until this point has been finding, for example, interpolating polynomials and best fitting least squares polynomials that pass through these points. Often, however, we are dealing with periodically varying data. Time domain analysis on a periodic signal is actually much more difficult. For example, best fitting quadratics even don't necessarily do well. They don't tell us anything about the periodicity. We could find a best-fitting linear combination of sine and cosine functions, but this would be very expensive and a little bit suboptimal, as we will see. So for example, suppose we have a periodically sampled periodic signal with noise. So for the last 8 readings, we have these values that were recorded. Now, suppose that we know that the signal is periodic and that the angular frequency is 0.32. All right. In that case, we can evaluate the t vector, or we can evaluate cosine of 0.32 times t for each of the values of the t vector. That's the first column. And then we'll evaluate sine of 0.32 times t for each of the values in the t vector in the second column. That gives us our Vandermonde matrix. So now all we have to do is solve v transpose times v equaling v transpose times the values. That will give us, in this case, these two values of a and b. So the best approximation of a linear combination of cosine and sine of this data is negative 3.4585 times a cosine minus 1.6166 times that sine. So we can take a look at the noisy data and, well, yeah, it may appear to be periodic. However, we can also then plot the least squares best fitting sinusoid. All right, so from this we can, for example, estimate the amplitude of this sinusoid. We can estimate the most recent 0, and we can estimate approximately when in the future this periodic signal will once again be 0, or, for example, reach a maximum. So this approach, however, is expensive computationally and very narrowly focused. It only works for a given frequency. And this is suboptimal if, for example, you're not aware of other frequencies within the data, or you may have multiple frequencies within a data, or there may be more noise or other issues at hand. So instead, what we're going to do is look at frequency analysis. We're going to transform the data from the time domain to the frequency domain, and so we will observe all of the frequencies within the data, not just, as the previous example showed, one particular frequency. Now, our approach will be as follows. We are going to review linear algebra and specifically the inner product, the generalization of the idea of a dot product. We will then look at complex exponential Fourier series. Now, you may have already seen Fourier series and you may have seen them with sines and cosines. However, we're going to see that dealing with complex exponentials instead is a much easier way and much more explanatory technique to analyze periodic functions. What this will do, therefore, is this will motivate a discrete Fourier transform on finite-dimensional vectors. Then we will look at an algorithm called the fast Fourier transform. Normally, the discrete Fourier transform requires n-squared operations for vectors in R or C to the n. However, the fast Fourier transform does this in n log n time. It's the same as going from insertion sort to quicksort. Now, recall the definition of a finite-dimensional vector. For example, a vector in R to the 8 is a real vector that has 8 entries. For example, here are 2 vectors in R to the 8. One of the most important operations we can perform is taking linear combinations of these vectors. So I can take 0.5 times the first vector plus 2.1 times the second vector. Now, there are other properties. We have a 0 vector, and vector addition is commutative and associative. And if we multiply a vector by the scalar 1, we get that vector back. If we multiply a vector by 0, we get the 0 vector. And if we add the 0 vector to any vector, we get that vector back. Recall that a function of t is a function f such that we can evaluate f at each value t on a given domain. For example, here are 2 functions for a real variable t. They are polynomials. Guess what? We can take a linear combination of these functions. For example, I can multiply the first function by 0.5 and add to that 2.1 the second function times the second function. That gives us another function. That's just what we did previously with vectors. But not only that, remember that if I multiply a function by 1, I get that function back. If there is a 0 function, the function that is just defined as 0 for every single value of t. And if you add the 0 function onto any other function, you get that function back. if you multiply any function by the scalar 0, you get the 0 function. It doesn't matter what order I add two functions together, I'm going to get the same result. So function addition is commutative. Also, it's associative. If I have 10 functions, it doesn't matter how I add them together, they will still ultimately come to the same result. What's the conclusion? Functions are vectors. Hopefully you saw this in your linear algebra course. If not, however, you should start to think, yes, anything, if there is anything that I can add two things together or multiply one of them by a scalar, if this all makes sense, chances are you can consider them to be vectors. What that means is we may be able to define inner products on functions because we have inner products on vectors. And then we can define projections, orthogonality. We're going to see all of that in the next topic. Following this topic, you now understand that all the analysis that we've done up until now is in the time domain. That is, we have sampled a signal periodically in the past, and we are analyzing that data based on the values that we read at those points in time. We have observed through an example that it's actually rather difficult to try to do frequency analysis in the time domain. For example, if we know there's only one periodic signal, we may be able to extract it. But that's difficult if there are multiple periodic signals. Instead, what we will do is we're going to transform the data from time domain to frequency domain, meaning that we will look at all frequencies that make up the signal that we have observed. And then we will analyze the frequencies and use those frequencies. So we described what we're going to see in the upcoming lectures. We will first review linear algebra and the inner product, the generalization of the dot product. We are going to look at the complex exponential Fourier series, and this will introduce to us the discrete Fourier series that then allows us to introduce the fast Fourier transform. But before we can do that, you saw a quick review of vectors, but you also saw that functions share these exact same useful properties. So if you're not aware yet, you now know that functions are vectors. They can be treated just like vectors. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!